Good afternoon, everyone. Okay, so I don't have any announcements today. If you have any questions, though, let me know. Post them in the chat, or feel free to come on, just talk if you can. I'm going to start out by going over quiz 6 that was due on Monday at midnight. I extended that because of some bugs I had on in the answer list for the last 2 questions. And I don't have another quiz right now. Hopefully I'll have one posted on Monday for you, and then you'll have till the following Monday. I'm hoping might be able to finish this lecture today, and then that'll allow us to start the next one on Monday, but we'll see how it goes. Okay, so the first question on the quiz was, which dopant can be used to create N-type silicon? And the answer there is phosphorus, because it's the only answer that is an element in column 5 on the periodic table. And so N-type silicon is the type that has electrons as the majority charge carriers. And so that electron charge carrier comes from the fact that the dopant comes from group 5, having 5 valence electrons, 5 electrons in the outermost shell. So if you dope with boron or gallium, for instance, those have 3 valence electrons, so there's a hole there. There's a lack of an electron, and so that would give you the p-type, positive type silicon. So just again, p-type is doping with a group 3 element. N-type is doping with a group 5 element. P stands for positive because the majority charge carriers are holes. N stands for negative because the majority charge carriers are electrons. Either one can be used to carry current. What type of silicon forms the body of a p-type transistor? The body is the substrate that the transistor sits in. It's kind of like the bed of the transistor. It's important that the body be connected to power or ground, depending on what type of transistor it is, in order to avoid there being leakage from the diffusion areas into the body, or from the source and drain into the body. So basically the body serves to electrically disconnect the source and drain from the substrate. So in the case of a p-type transistor, it's the source and drain, or the diffusion areas, same thing. Source and drain are the diffusion areas. They're p-type silicon. They're p+, so they're highly doped p-type silicon, and the substrate is an N-type, so the substrate is the opposite type as the transistor. And in the case of a p-type transistor, you don't actually build the transistor directly into the chip substrate. You actually build it into a well, which is a localized region of the opposite type of silicon to the substrate of the chip. The well in the case of a p-type transistor would be connected to VDD.
Dr. Bakos, I think someone in the chat said that the slides are cut off.
Which is shown over here, this N-type. This is just a contact. Basically, it contacts VDD, and it allows a path for a connection between VDD, which ultimately would be a metal rail or metal wire, and that would connect through this diffusion area, and it would electrically connect the N well to VDD. And since that would be a high voltage, you wouldn't have any current going from the well into, or the only way that you could have current flow, because current flows from higher voltage to lower voltage, and since the N well is the higher voltage, the fact that that is the higher voltage and the P is lower would mean that the diode formed between the diffusion area and the well would be reverse bias, so that would disconnect the well from the source and drain. However, as we found out, it does still create a capacitor, unfortunately, but it doesn't create a connection. The N well is sitting in the substrate, which is p-type, which is going to be grounded, and so that also ensures that the well to substrate is also reverse biased. Hopefully that makes sense. I know it's normally you would teach this material in a class where you were actually doing layout as well, like a VLSI design class. But I decided to put this kind of a brief introduction to this material in this class to give you an idea of what sort of factors influence performance, since typically cyber physical systems are performance limited, performance constrained. Okay, so what type of transistors comprise the pull-up network? That's P-type. P-type is always pulling up, N-type is always pulling down. Pulling up is basically just means connect the output to VDD. Pull down means connect the output to ground. Sorry, pull up is connecting the output to VDD. Pull down is connecting the output to ground. The pull up and pull down are, only one of them is active at a time, or should be. If you think of transistors as switches, but as we saw, like if you look at a sort of a curve where you plot the V out as a function of V in, there is a point in the middle where technically both the pull up and the pull down are technically turned on, but turned on in that region usually means they're saturated. So the amount of current is limited, but it's still not trivial. There's a lot of current that flows when you're sort of in that halfway point between 0 and 1 on the input, and so that's where most of your energy is spent on a CMOS chip is during the transition from 0 to when the output transitions from 0 to 1 or 1 to 0. So the PMOSs are pull up because what is the reason for that? Well, the reason is that the PMOSs you want those to be closer to VDD, so that way the gate voltage is relative to the source, right? The VGS, and so you want the source at VDD because the gate voltage, gate source needs to be negative to turn them on. If you had the PMOSs in the pull down network, the source would be at ground, and it would be tough to make those make the gate negative. So that's basically the idea. So PMOS pull up, NMOS pull down. MOSFETs are defined as P-type or N-type according to the type of their diffusion area. Didn't we already have that question? Oh, yeah, we had the body. Okay, yeah, sorry. The earlier question asked about the body of the P-type of the transistor. So the body is of the opposite type of the diffusion areas, and the type of the transistor is named after the type of silicon in the diffusion area. So, and for example, and this is what I'm showing here is a P-type transistor. The diffusion area is, I'm sorry. No, sorry, scratch that. This is an N-type because the diffusion area is N-type. Yeah, sorry, I got tripped up because I was looking at the question. So the question says they're defined as P-type or N-type according to the type of their diffusion area. So if the diffusion area is N, then they're N-type. If the diffusion area is P, they're P-type. Okay, which of the following Boolean functions can be realized with a single CMOS gate? So these are 4 different 2-input Boolean functions, and I give the truth table for each one of them here. I didn't give the truth tables in the question on the quiz. I just gave you the Boolean expression, but I'm giving you the truth tables here because those are relevant to the question. So in order to answer this, you have to ensure that when the inputs are all zeros, that means that there's no way to pull down, right? So if the inputs are all 0, there's no way to turn on an NMOS transistor, and the NMOS is the pull down. So if you look at the rows of the table where the inputs are zeros, then the output cannot be 0, right? So so that's a problem on this guy, right? Because A is 0 and B is 0. That would turn off the NMOS transistors, all the NMOS transistors. And since the NMOS transistors are responsible for setting the output to 0, then how can the output be 0? The output can't be 0 if you don't have any NMOSs that are turned on. On the other hand, the PMOSs pull up, and the PMOSs turn on when they're 0. So if the inputs are both 1, there's no way that you can have a 1 output, right? So this guy has a 1 output, right, when they're both on. This truth table, but the second and the fourth truth table. So so of the 4 Boolean functions, or the 4 Boolean expressions in their truth tables, 3 of them have a row that violates the pull down or pull up rules. So the second one and the fourth one need to set the output to 1 when the PMOSs would both be off, and the third one is trying to set would have to set the output to 0 when the Nmoss are off. So so those are impossible. You can't make those. The first one is not A and not B, and actually that's just the equivalent to a NOR gate, because that's just the De Morgan's law version of a NOR gate. So you have A or B, and then the whole thing inverted or complemented. And then that's equivalent to complementing the inputs individually and then changing the OR to an AND. So anyway, so this is first one's a NOR, and the other ones can't be made with 1 gate. Now you can still make these functions, it requires more than 1 gate. That's all. You just can't do it with 1 CMOS gate. Okay, what is the operating region of an NMOS when the VDS equals VDD and VGS equals VT? So what this is saying is that the voltage drop over the transistor is VDD. That's basically, that's a big voltage drop. Normally in a CMOS gate, you don't have a huge voltage drop over the pull down or the pull up transistors because you're actually pulling the output either up or down, which closes the gap between the output voltage and the other side of the pull up and pull down network. You know what I mean? So if you pull up or pull down, you're basically making the drain source voltage very small. I mean, that's the whole point of pulling up and pulling down. But in this case, I'm saying, well, what if the drain source voltage is essentially the maximum voltage potential drop you can have, which is VDD, and then assuming the VGS is VT. Well, normally if VGS is VT on an NMOS, that would mean that you're turning the NMOS on, but when it's on, it can either be in saturation mode or it can be in linear mode. The difference is that when you have a large voltage drop over the drain source, that's the definition of saturation mode. Is you saturate when you try to put a large drop over a transistor that's turned on, because transistors are fundamentally limited in how much current they can conduct from between the source and drain. Now that depends on the width. So the wider that limit is going to depend on the beta term. So you can have more current flow through when it's in saturation mode, based on the width of the transistor, but saturation mode is the cutoff point for a given transistor. So so more specifically here, the cutoff is when the gate source is less than VT. Linear mode is when the gate source is greater than VT, meaning the transistor is on, but the gate source is greater than the drain source voltage. And then the saturate. So basically, the gate source greater than drain source. So your gate source exceeds your drain source difference. And this is why, by the way, when you're pulling up or pulling down, you're expecting the pull up and pull down to be in linear mode when you're pulling up and pulling down. Saturation mode happens when you're doing your transition. When you're transitioning a gate from 0 to 1 or 1 to 0. And saturation mode happens basically when you have a large voltage difference over the transistor and it's turned on. So that's when the drain source voltage is greater than the gate source minus the threshold. And so saturation is in this case, we'd be in saturation mode. What's the beta value for a transistor with width equals 1 micron, length equals ½ micron, capacitance of the oxide 2 femtofarads, and mobility equals 2 centimeters squared over volt seconds. Yeah, the mobility unit is kind of crazy. So pretty much it's just the width over the length, which is 2, right, multiplied by the capacitance multiplied by the mobility. So you just take the ratio of width to length and multiply it by the other two numbers. So it's 2 times 2 times 2 is 8. The problem is that what are the tricky part is what is the scale, though? What is the significance of the answer? And that's the tricky part. So centimeters is 10 to the negative second meters. And then width and length are micrometers, microns, which is 10 to the negative 6. But that doesn't matter because those are, you're getting the ratio of those. So that unit drops out. And then femtofarads, that's 10, femto is 10 to the negative 15th. So it's basically 10 to the negative 2 times 10 to the negative 15th, which is 10 to the negative 7th. And I didn't put the units in there. The units are, you can figure out the units. The units are given. Okay, consider an inverter whose PMOS widths are 2 minimal units, and its NMOS widths are 1 minimal unit. Okay, so minimal unit would be, you know, the size of the transistor. Minimal unit of the NMOS transistor. Well, technically, the PMOS and the NMOS can both be 1 minimal unit. I mean, you could make it. It wouldn't violate any design rules, I don't think. But no one makes a PMOS a minimal unit. Usually, the smallest PMOS is 2 minimal units. So let's see. The inverter, right? So you've got an inverter that's pretty much set up in the standard way. PMOS is twice the size of the NMOS. Minimal size inverter. But it's driving 4 copies of itself. So what's its propagation delay? Assuming that it has a unit resistance and capacitance C. Okay. So so this is a simpler case than having to have gates, because the inverter has the effective resistance of R, which, you know, again is an effective resistance, because really the real thing you're calculating there is the current. But it has an effective resistance R, and then it has an output that has capacitors on the diffusion areas of the pull-up and pull-down transistors. So those would be 3C in total, because, you know, you've got 2C on the PMOS and 1C on the NMOS. And then it has a load. And the load is going to just be the gate sizes of the PMOS and NMOS on the load transistor, which is, again, 3C in total, but that would be multiplied by 4 because it's driving 4 copies of itself. So the answer here would be R times 15C. It's, you know, 3 from the output and then 12 from the inputs, right, of the transistors or the inverters you're driving. So 15 in total. Now this is okay. So first of all, you might see this term called Fo4. So every fabrication process has an Fo4 delay. The Fo4 is basically this. It is, if you have a minimal size inverter that's 4 copies of itself, what is the delay? How fast is it? And you can define that, or you can come up with that number in seconds for any process. And that kind of gives you an idea of kind of like it's kind of a metric that kind of defines how fast a given fabrication process is. So so yeah, that's Fo4. Now the other thing is that this is a little naive, though, because we're assuming that there's no resistance in the wires or capacitance for that matter. So in the next lecture, I'm going to talk about wire resistance and capacitance. In this case, we're assuming that there's none. So there's no, you know, we're just assuming that there's no resistance or capacitance in the between the output of this guy and the input to its, you know, four target inverters. Okay, and then this one is this is question 9. Consider a 2-input NAND whose PMOS widths are 2 minimal widths and its NMOS widths are 1 minimal unit. Sorry, 2 minimal units and 1 minimal unit for PMOS and NMOS. This is actually how I used to design my gates. But as I mentioned in the lecture, you probably you might not necessarily want to do it this way. You might want to make the NMOSs a little bigger just because you've got 2 of them in series. But for this question, just assume we have it set up with 2 and 1. And this guy is driving 1 input each of 2 copies of itself. So it's kind of like the Fo4 delay, but it's just basically with a NAND gate, and it's only 2. The output's only being fanned out to 2 inputs. So what's its falling propagation delay, assuming it has unit resistance R and unit capacitance C? So in this case, we have to use the Elmore delay to calculate this. So with the Elmore delay, you first have to come up with a circuit design for this guy. Now, I said falling propagation delay, so we only consider the pull down parts. But the thing that's confusing about this is that even though we only care about the pull down, you still have to consider the impact of the diffusion capacitance for the pull up transistors, because they are connected to the output line. So that part is a little, I don't know, might be a little confusing. So let's see. So we've got 2C and 2C on the output, right? 2C capacitor, 2C capacitor. That's the diffusion area of the 2 transistors that are in parallel on the pull-up. You have 2 parallel NMOS on the pull-up network. Why? Well, it's because it's a NAND. A NAND, you know, with a NAND, if either input is 0, it's going to pull up. Just like with a regular AND, if either input is 0, then you're going to get a 0 output. But NAND is the opposite of that. So NAND is any zeros will give you a 1 output. So that as a result, because zeros turn on PMOSs and PMOSs are in the pull up, you're going to put those in parallel. The NMOSs and the pull down are in series because you have to have 2 1 inputs in order to pull the output down. Okay, so the pull-up transistors have 4 units of capacitance in their diffusion area, and then the first NMOS in series has 1 unit of capacitance in its diffusion area. So you've got 5 units of capacitance just in the diffusion areas of the transistors connected directly to the output. And then you've got 2 resistances in series pulling down, which is the reason why you probably wouldn't want to use a minimal size NMOS for this, because your effective resistance here, of course, would be 2R to pull down, which, you know, isn't great. And then you have 1 capacitor in between the 2 NMOSs for the diffusion area in the connection, in the serial connection. Now you might say, wait a second, hold on a minute. If each transistor has 1 C in each of its in each of its diffusion areas, then aren't there 2 diffusion areas that are linking these 2 guys? Isn't there 2? There's 2 transistors. You're basically connecting the source of one to the drain of the other, right? That diffusion area that's in between the 2 NMOSs, that should give you 2 units of capacitance, should it not? Yes, that's a good point, except that typically the way these are designed is that they would share 1 diffusion area. And I should have made that point. I should have clarified that actually last lecture. I just thought of that. They would be sharing a diffusion area. Transistors that are in both series and parallel transistors can share diffusion areas. So there's not necessarily 2 separate diffusion areas. They're merged into 1. So that's 1C. And then the inputs to the each input to the NAND gate has 3 units of capacitance because you fan out to both the Nmos and the PMOS, and so that's 3 units in total. And if there's 2 of them, then there's 6 units. So you got 6 units here. Okay, so now we have to calculate the Elmore delay. So to do that, you have to start with the voltage source, which is the output of this guy's ground, is the voltage source. So you go through 1 unit of R with C, so that's RC. And then you add to that 2 units of R to get through both resistors, and then its total capacitance, which is going to be 2 plus 2 plus 1 plus 3 plus 3. So that's 5 plus 6. Right? Did I do that wrong? That's 4, 5, right? 2 and 2 is 4. That's 5. Okay, so that's 5, and then that's 3 and 3. That's 6. So that should be 11. Dang it! I think I screwed that up again. Okay, well I'm going to give everyone credit for this one. Yeah. Oh, except that there's also 2R there because you're going through 2, so there's a multiplier of 2, right? But still, that should be 11C, not 13. Okay, so yeah, I screwed that up again. I don't know how I did that. So that should be not 7. That's 2 plus 2 is 4. That's 5. Yeah. Okay. Sorry about that. Okay, so yeah, that should be 11, right? So that's 2, 2, 2. Okay. And then, so then the last question is 2-input NAND, basically the same idea, except now rising contamination delay. You might say, well, why did you do rising? Why not falling? Well, falling contamination delay should be the same as the propagation delay, because anytime you pull down, you're going to have to go through the minimal amount of resistance to ground when you pull down is 2R. There's no way to avoid that. But because the pull-up network has 2 parallel resistors, then if they were both on, you would have only a half a R. But if only one of them is R on, you'd have 1 R. So the contamination delay is kind of the fastest pull-up time, which would happen if both resistors were on. The effective resistance was 1/2, so that would be R over 2. And in this case, you don't have to use the Elmore delay because the resistors here are in parallel, not in series. So as a result, you can kind of just collapse these 2 resistors into one with 1/2 R. And then the total capacitance, and hopefully I didn't add these up wrong too, that would be 1 plus 2 plus 2 is 5, plus 6 is 11. Yeah, so 11 over 2. RC. So that one I had right. So now you might, what would be the propagation delay? The propagation delay would be basically the same thing. The only difference is the R would just be R instead of R over 2. So the contamination and propagation delay are quite different. The contamination delay is half the propagation delay. You might say, wait a minute, if only one pull-up transistor was on, wouldn't you delete those capacitances on the second one? No, because it doesn't matter if this transistor is on or off, you still have the diffusion area capacitance. So, I mean, well, technically this one here is from the Nmos, and then these 2 are from the PMOS, but they're in parallel. So it doesn't matter if you can have just one transistor on pulling up, you still are affected by the diffusion capacitance of the other one. So the capacitance is still going to be 11C, so the resistance will be either R or R over 2. So yeah, basically there's a big gap between contamination and propagation. Now, if you guys, when you guys take my 611 course, I have a lecture in there about timing closure, where you dealing with, guaranteeing that if you have a circuit with memory elements in it, flip-flops, there's this idea of a setup and a hold time. and those have to be guaranteed throughout the range of delays you get, where the range of delays is going to span from the contamination delay of all the gates along the minimal path versus the propagation delay of all the gates along the critical path along this path. And so if the minimum amount of delay is too low, then you violate the hold time, and if the maximum amount of delay is too long, you violate the setup time. So yeah, so that's a topic I do in 611 under time enclosure, and that's why this is important. But in this case, we only are looking at why there's a difference between contamination and propagation delay. Okay, so good. If there's no questions. Oh, sorry, I didn't hear the other questions. I was on mute. Oh yes, sorry guys. Yeah, sorry, shoot, I'm still getting used to this. Sorry. Okay, let me try something here. Sorry. Let's first of all. Yeah, I'm sorry. I've been in meetings all day. I'm a little out of it. So I forgot to readjust my resolution. So hopefully this fixes the cutoff problem. And then as far as the other question, I think someone asked about the 5 plus 6. Yeah, 5 plus 6. Yeah, so someone asked about that. And then why isn't the left-hand side of the NAND 6? 6. Question 9. Yeah. So I'm on question 9. Left-hand side of the NAND. Why isn't it 6? 6. 6C? 1, 2, 3, 4, 5. That's 5, right? So there's 5C here, and there's 1C down here, right? So let's see. So yeah, there's R. So you have RC here, and then RR to the other C's. So that would be 5 and 6. So that should be 11. So I think I've got that right. Does that make sense, Matthew? Okay. Yeah, sorry for the bug. I'll go ahead and I'm going to give everyone credit for that. I apologize for that. Okay. All right, good. Let's switch over here to, and I'm sorry the slides were cut off again. I like I said, I have to always adjust my Blackboard doesn't work well with 4K screens. Hopefully you were able to see enough of those. I will post these slides on Blackboard in case you want to see the solutions. And there'll be the the corrected version of question 9. Okay. Switch slides now. Okay, so you should see the second slide deck. It hasn't popped up yet. There it is.
Daddy, it's almost, my watch is almost to die.
Final answer should be 23. Yeah, so let me double check that. 23, yes, thank you. Thank you. Yeah, so that should be 22 plus 1, 23. Yep, thank you. Okay. Okay, all right. Okay, here we go. So the next lecture is about interconnect. So so previously we looked at delay, but we looked at gate delay. We didn't consider interconnect delay. Interconnect is the wires that connect the gates. Those have a significant impact on performance and power. So basically what I showed before was a little misleading in the sense that I didn't consider the wire delay, but we can add the wire delay to the gate delay. In practice, I think these days the wire delay is usually higher than the gate delay. Yeah, so it's a major factor. Okay, so so what do we need to know about wires? Well, ultimately, we need to know the resistance and the capacitance. It works just like gates. I mentioned that wires also have inductance, and you know, so there's inductance everywhere. But when you're talking about when you're modeling of wires on a chip, you usually don't consider the inductance usually has a minimal impact. However, if you're modeling the delay of longer wires that go off chip, like, you know, longer, bigger wires that, you know, that would connect the chip to other chips, or you know, connect boards like in a network. The inductance there is much more significant, and everyone will always consider, so they'll model, you know, long wires with RLC as opposed to just R and C. But we won't worry about that in this lecture. We're just concerned about the resistance and capacitance of wires, and once we know those, then we're just going to use the Elmore delay, just like we did for the gates, to model it. So really the only question is, how do you get the resistance and capacitance of a wire? Where does it come from? How do you calculate it? So it depends on the shape of the wire, the length, the size, the thickness. It's hard to, you know, that's hard to, obviously you don't know what any of those things are until you actually design your chip. So generally, once you design the chip, you use a process called extraction, which will extract the capacitance and the resistance from the layout of the chip, from the design of the chip. And then you can simulate the extracted designs in a circuit simulator, which would include the transistor models, the transistor behaviors, as well as the parasitics, which are the unintended capacitances from the design of the chip. But you have to, you know, wires are technically, you know, they're 3D structures. Even though when you design them as a 2D from the top down. So the first thing you have to consider is the thickness of the wire, which is a function of the fabrication process. And so you can see that they're pretty thick in practice if you look at them from the side. So you have to consider that. I'm getting a little ahead of myself. Yeah, let me start with this. So wires are made out of a metal. So when you look at it, like if you look at a chip, a processor, what is it? What is it made out of? Well, it's silicon forms the bottom part of the chip, the substrate and the diffusion areas and the wells. Those are called the active layers. So that's at the bottom. But then you have layers on top of that. You have layers of metal that are separated by oxide that isolate each layers. Chips typically have, you know, 6 to 8 layers of metal, and you might say, well, why you need so many? Well, because as architectures become more complex, they require a higher level of interconnectivity, and the level of interconnectivity drives the number of metal layers you need in order to connect everything. You can have a lot of transistors on a chip, but if you don't have enough you know, routing tracks to connect them all, then it limits you. This is why, by the way, I don't know if you guys know this, but like if you look at the x86 instruction set, the Intel instruction set, they developed that back in the 70s, the late 70s. And one of the things that you might notice from it, if you're used to programming in MIPS or in RISC-V, which are newer instruction sets, is that the Intel instruction set uses 2 addresses. It's a 2-address architecture. Like when you add, you want to do an add or a multiply, you only give it 2 registers, and the result is put in the first. So you give it 2 registers that serve as the operands to the multiply or the add or the divide or the subtract, and then the result is put in the first one. And if you look at that, having taken 212, you guys are all master MIPS assembly code writers now. You know, you might look at that and say, well, that's kind of dumb. I mean, MIPS has a destination register and has 2 source registers. Why would Intel, which is presumably has the fastest processors, in the world, why do they have 2 register addresses? And it turns out that the reason for that was because when they originally designed it, they had limited metal layers, and they couldn't design a 3-address architecture because they didn't have enough. They couldn't have enough wires to connect all the 2 operands and make them separate from the destination. They couldn't get enough wires in and out of the register file to make that happen. So internally inside the register file, they had to make the first operand also the destination, because they literally just didn't have enough wires to connect everything. And then of course that, now obviously that's no longer the case, but Intel has a philosophy where they don't change their instruction set. And so when you look at their instruction set these days, and if you write code in an Intel assembly language, you're literally writing code and having to use two address instructions as a result of fabrication limitations from 50 years ago. It's kind of crazy. But anyway, as metal layers were added, instruction set architectures were able to switch to, they were able to take advantage of those metal layers to do things like 3-address and pipelining and all the other neat stuff that you can do in an architecture now. Okay, so where was I? Okay, so anyway, so wires are metal. What kind of metal? Well, originally they were aluminum, but starting about I don't know when it was actually, 10, 20 years ago, they switched to copper. And because copper has better conductivity, as copper has a bulk resistivity of 1.7 ohms per centimeter versus aluminum 2.8. So almost twice as conductive. And resistance translates directly to speed, right? I mean, so because the delay is RC, so obviously you want the more you can push the resistance down, the faster the chip is, the faster the propagation delay goes down, the faster you can run the clock. Unfortunately, copper has some horrible side effects. Copper atoms will actually leach into the silicon. So in order to do copper wires, they had to come up with this way of insulating them with a layer of silicon around them, or polysilicon around them. Also, copper has this thing called cupping, where you can't make the surface of the copper flat because it kind of dips in. So there's a bunch of challenges related to that, but most of those have been kind of worked out, and now chips use copper for their wires. So as I mentioned, these different metals have different bulk resistivities associated with them, or sometimes just called resistivity. And that is expressed in terms of microohms per centimeter, or microohm centimeters rather, which is an odd way to do it. What does that mean? So ohms times distance is the unit. That's usually represented as rho. Once again, we have a rho. That's the resistivity. So basically what the bulk resistivity is a way to represent how conductive a metal is, basically in one dimension. But unfortunately, things are 3-dimensional, right? So you have to, but you can convert, once you have the bulk resistivity, which is rho, all you have to do is divide that by the thickness of your wire, which is T. So that gives it the second dimension. And then you multiply it by the ratio of length to width to give it the third dimension. Now this is assuming, you might say, wait a second, whoa, why is width in the denominator and length is in the numerator? Well, the assumption is that the current is being sent down the length of the wire, right? So if the directionality of the current is down the length, then having more width will reduce that resistance as current flows down through the length. However, as you make the length longer, the resistance will rise. So you make it longer, you get higher resistance. You make it wider, you get less resistance. And if you make it thicker, you get less resistance, which is why the damn things are so thick. They're ridiculously thick. They make them as thick as they possibly can when they make these chips, because that directly, it divides the resistance and directly translates into speed. So of course you want them as thick as you can. The thicker, the better. So the total resistance of a wire then is going to be rho, which is your material resistivity, divided by the thickness, of course also divided by the width, but multiplied by the length. Now, a lot of times they'll take the rho. See, the thickness is usually fixed, though. As a designer, you know, just like the oxide thickness, you know, when you calculate beta for a transistor, you can't control the thickness. That's something that TSMC or Samsung or Global Foundries or you know, whatever company, Intel, that whatever company is making the chip, they're going to tell you what the thickness is. You can't control that. That's part of the fabrication process. Likewise, rho, you can't control that. So you might as well take rho and T and just put them into just their own constant, you know, term, their own magic number, as Charles would call it, which is called the sheet resistance, which is shown as R sub square, which is R sub square. R sub square. Yeah, that's the sheet resistance, literally square. This is the first time I ever seen a square used as a mathematical symbol. But yeah, believe it or not, it's R sub square is the sheet resistance. So that's rho over T. Those are, you know, that's the thing you can't control. And then the width and the length, though, you control that. As a designer, you can draw your little polygon and make wire of any size that you want. Now, typically, the width is usually minimal width. Usually. There's a minimal width for every metal layer, and usually use minimal width wires, but you don't have to. You can make them thicker if you want. So the resistance is just the R sub square times the length over the width. And then so like if you count the number of squares, then you know, multiply that by the sheet resistance, you get the wire resistance. That's pretty much it for the resistance. We still got to get to the capacitance, but the resistance is pretty straightforward. It's just essentially once you know the bulk resistivity of your metal, and of course the layout of the wire, you're good to go. So for example, here's an example question. Compute the sheet resistance of a 0.22 micron thick copper wire in a 65 nanometer process. The resistivity of thin film copper is 2.2 times 10 to the negative eighth ohms times meters, ohm meters. So the sheet resistance would just be the resistivity divided by the thickness. You might say, wait a second, why is 65 nanometers relevant here? It's not. It's not. It's just designed to mislead you. So that would give you 0.1 ohms per square, and then find the total resistance of the wire. If it's 0.125 microns wide and 1 millimeter long, so the 1 millimeter is 1,000 microns. Divide that by 0.125 microns, and that gives you your, you know, your aspect ratio. You multiply that by the sheet resistance, and that's going to give you 800 ohms. That's pretty simple, right? Okay, now capacitance is a little bit harder, though. So you might first ask, why would a wire have capacitance? What is, like, where's the capacitor? Like, how is it formed? Like, a wire is one terminal, a capacitor is two terminals. So what's the deal? Well, that part's kind of complicated. So wires run along the surface of the chip, and as I mentioned, they're running over top of the substrate and the wells. So effectively, you know, the substrate is grounded, right? So and there's an oxide layer that protects the substrate from the wire, but it also forms a capacitor. So basically that wire is essentially one layer of one side of a capacitor. The other side would be the bottom of the chip. Now you may also have something above it. You may have a layer above the wire, although normally you don't have that. Like in a circuit board, you would have ground and, you know, ground planes, VDD planes, but in a chip you usually just have kind of a ground plane, which is essentially the substrate of the chip. But you also have capacitance to wires around the wire, like adjacent wires, neighboring wires. So you have to consider that. So you've got like a capacitance to the bottom, the capacitance to the top, and then you've got adjacent capacitances to the neighbors. So as you can imagine, that is very hard to figure out because that is all dependent on the design. You know, for example, the distance, the height, H sub 1 there, which is the height of the wire above the ground, the layer n-1, is, assuming layer n-1 is a ground plane, that would be, you know, that would be dependent on like what layer the wire is on, because there's multiple layers. So as you go up in the layer stack, you're going to get farther away from the substrate. But then the neighboring wires, you know, that's obviously, you know, that depends on if you routed any wires next to that wire. So that's pretty complicated. Like how do you figure that out? Well, you know, you can't really, but you can kind of generalize it a little bit. So there's this formula in the book that says the total capacitance is the oxide dielectric constant, also called permittivity. That's epsilon ox times the length of the wire, and then you multiply it by width over height plus 0.77 plus 1.06 times the width over the height to the raised to the 0.25 power, so basically the fourth root, plus 1.06 times thickness over height to the 1/2 power, which is the square root. So what is that? It's an approximation. That's a function of the width and height of the wire, and of course the length, and the oxide permittivity. It's an empirical formula that, so basically someone went and measured this and they, you know, they curve fit it. And they say it works well for wires that have an aspect ratio of, you know, less than 3.3. The aspect ratio, of course, has to do with how thick the wire is relative to the width. So aspect ratio of 3.3 is a really thick wire. But I guess in this day and age, I don't know if they might be thicker than that now. I'm not sure. Yeah, so that's it. That's, of course, that only, you know, that's only considering the bottom plane. So that's essentially height 1 in this figure. It doesn't consider height 2, it doesn't consider layer n+2, and it doesn't consider the neighboring wires in the same layer. So yeah, that's a kind of that's a limitation. But it's you know, it'll give you an idea, and it gives me, you know, something to ask a question about on the test. Okay, so once we have this stuff, now we can finally come up with a complete delay model for like a gate that's connected to another gate with an actual wire, as opposed to, you know, a make-believe type of connection. So estimate the delay of a 10x inverter. 10x inverter, 10 times larger than minimal size inverter, driving a 2x inverter at the end of a 1 millimeter wire. Now notice it says of the 1 millimeter wire. Why does it say that? Because it's referring to the wire that we solved this problem on. So it's using an 800 ohm resistance, right? So that's the same wire we were talking about before. So there's 800 ohms there. So you see the 800 ohms. Now, you know, you look at this design and they've got a driver. The driver is the inverter, but it's modeled as just a resistor to ground. So, so basically, it's just we're simplifying the driving transistor to a resistor to ground. So this is obviously pulling down. The load is, you know, 2 femtofarad per micron oh, sorry. Let's see. Unit size inverter has, yeah. So remember that a normal inverter has 3 units of capacitance for its inputs, for its input. There's only one input for its input, and because it's a 2x inverter, that means that we're going to double the capacitance. So it's going to be 6 units of capacitance, because it's a double size inverter that we're driving, and the C is 0.1 femtofarads, so it's going to be 6 times 0.1, so 0.6 femtofarads is our load. The driver has 1,000 ohms because a unit size inverter has an R of 10 kiloohms, so if it's a 10x inverter, we're going to divide the resistance by 10. So instead of 10 kiloohms, it's 1 kiloohm. So that explains our driver, and that explains our load, and we also know our wire resistance is the one that we calculated. So what about the wire capacitance? You might say, why is there 2 capacitors there? Well, that's because I skipped the slide that talked about that. So the wires, so here's the problem with this wires. The wires are a distributed system. So the wire is going to have a different amount of resistance depending on where you are along the wire. And the capacitance will also be different depending on where you're in the wire. So basically, the number of states that are in a wire is infinite, because there's an infinite number of positions on that wire where you could measure the resistance and the capacitance at that point. And so basically, that means that you can't, you can't really model the wire perfectly, because it would require that you have an infinite number of states. So in order to get around that, they use a lumped model. A lumped model is where you subdivide the wire into a discrete number of units. You decompose it into a discrete number of segments, I should say, and each segment has its own capacitor and resistor, and that way you get a finite number of evaluation points along the wire. And you might say, well, that's, you might think, well, that sounds odd. Well, it turns out that everyone does it that way. This doesn't apply to wire modeling. This is the way how you do heat transfer equations, and almost any type of simulation of any physical system requires that you discretize points on the system, and they're the lumps, basically. You call them lumps. Now in this case, how do we model each lump? Well, you could do it, there's 3 different ways you can do it. You can do an L model, which is a resistor and a capacitor. It's kind of the most straightforward way. Resistor is in series, capacitor is in parallel. There's a pi model. Pi model is named pi model because it looks like, the circuit diagram for it looks like pi. In that case, you have 2 capacitors on either side of the resistor, and the capacitors are half the capacitance. So you divide the capacitance in half. You divide the capacitance of the lump in half, and then you put it on either side of the resistor. And then there's a T model, which gets its name because it looks like a T. And in that case, you have 1 capacitor and you have 2 resistors on either side, each of which having half the resistance. You can use any of these. However, generally speaking, most people use for this purpose, they use the pi model because it's the most accurate. I mean, it's the most accurate given a fixed number of lumps. So if you go with a certain number of lumps, like 10 lumps, then the pi model will be the most accurate for a given number of lumps. You can get equivalent accuracy with the other 2, but you need a lot more lumps. So we're going to use the pi model. Now, how many lumps do we need in the wire? Well, if you're modeling a long wire, like on a network segment, the answer is lots of lumps. But if you're modeling a wire that's relatively short on a chip, you can get away with just doing 1 lump, which we'll do. But obviously, the more lumps, the more accurate. More accuracy you get with more lumps. But as you add lumps, you add complexity, and when you simulate this thing in a circuit simulator, it requires you to evaluate a partial differential equation, which gets expensive as you scale up. So we're just going to use single lump pi model, and then we're going to use that to do Elmore delay, just like we did before. Elmore delay is essentially multiplying R times C, but you have to go through multiple R's potentially to get that, to get all the different RC terms. Okay, so right, so that's why if we go back ahead to this guy again, you can see that there are there's an 800 ohm resistor in the middle of the pi model, the pi lump, and then there's two 100 femtofarad capacitors on either side. Now, where do we get 100 femtofarads? That actually came from, that was the capacitance that we calculated, which was, did I delete the slide that calculated that? Assume, oh yeah, it just says assume the, okay, it gives you the wire capacitance. Assume the wire capacitance is 0.2 femtofarads per micron, and the wire is 1 millimeter. So you have to, there's 1,000 microns in a millimeter, and so that gives you 200 femtofarads of total capacitance, which then you divide into two capacitors on either side of the resistor in order to achieve the pi model, the pi model lump. And so the propagation delay in this case, now this would be the falling propagation delay because of the driver is pulling down to ground. So that would be 1,000 ohms times 100 femtofarads, which would be the first segment of the Elmore delay. And then you have to add to that 1,000 plus 800 ohms to get through both of these resistors, and then multiplied by the capacitance on the other side, which would be 100 femtofarads plus 0.6 femtofarads. So you evaluate that and you get 281 picoseconds. So that's the delay, the falling delay. For that includes the inverter, the wire, and the load. So that's it. That's all the delay stuff. So we have a couple of things we want to talk about though before we finish up this low-level CMOS stuff. The first thing is really quick. It's energy. So I mentioned that there is static and dynamic power. Dynamic is from switching outputs of gates from 0 to 1, 1 to 0. Obviously, that's because during that time, both pull up and pull down go into saturation, and so they're both on, and you get a lot of current. There's also static power consumption, which is the leakage you get through the pull up and pull down networks, even when the gate is not switching. And you might say, how is that possible? Wouldn't both gates, wouldn't one gate be in cutoff mode? How can you get current through a gate in cutoff mode? You can if you lower the voltage down towards the threshold, the power supply voltage. And that's the way they've been going. They keep bringing the voltage down. Why is that? Because the power consumption is a function of voltage squared. So if you bring that voltage down, you get a huge benefit in terms of your power consumption. And in the case of, semiconductor manufacturers have a huge incentive here because customers expect, that there be new capabilities, always new capabilities. And the only way to deliver that is to, you have to continue pushing the packing more compute, and to do that, you have to stay within a power envelope. You can't really exceed essentially 1 watt. Like even for a server processor, you're limited to about 2 watts per square millimeter of chip. You can't go beyond that, or you end up with too much heat dissipation in too small of an area. So you basically have an envelope, you have a limit, and to stay within that limit, even in the face of increasing amounts of capabilities or number crunching and operations per second, you need to bring that voltage down. But you bring the voltage down, and you get that voltage down to near threshold, and all of a sudden you now have leakage. You got a lot more leakage current. So basically, voltage squared is the power, but it's also, if you're doing dynamic energy, you multiply that against the frequency because you're worried about, you're looking at switches per second. Now you might say, wait a second, hold on. The frequency, the clock frequency of a chip is the clock frequency. That doesn't mean that every wire is going to be switching at that frequency. I mean, sometimes chips just sit idle, right? It's true, but they usually use the F as kind of a, as a generic, idea of, at what rate do you expect bits to flip? That's F. So flips per second. And then capacitance is the capacitance. That's also part of the energy equation. So hopefully you guys are familiar with this equation from 212. That should have been covered in 212. Now when it comes to wires, you've got voltage, you've got frequency, and you've got capacitance. So you got all the same. You can apply this just to a wire as opposed to like a whole chip. If you're doing it for a whole chip, you would have the total capacitance. But for a wire, it's just the capacitance of the wire. And so, so that would be the capacitance times the voltage squared, and then the frequency. If you multiply it by the frequency, that's going to give you power. But if you want energy, you drop the frequency, and that would give you essentially the amount of energy per bit flip. So in this case, you drop the frequency, so it's 0.2 picofarads per millimeter times 1 volt squared. So, and notice that the capacitance is in terms of, farads per millimeter. So this would be 0.2 picojoules per bit. Bit is in there because we dropped the frequency. That's the bit, bit transitioned per millimeter. And the per millimeter is in there because the capacitance was in terms of picofarads per millimeter. So this would give you 0.2 milliwatts per gigabit per second per millimeter if we then multiplied this by, a billion, essentially. So pico to milli is what you get from multiplying by a billion, 10 to the 9th power. Yeah, so that's the energy. Okay, and last topic is crosstalk. So I talked about the fact that you've got capacitance between wires and adjacent wires. Capacitors make it so it's difficult to change voltage, right? Now, so normally you have these capacitors to ground, right? And so when you have switches, you have a wire that's above a ground plane or above the substrate, and it's switching, you generally expect that the ground part is going to stay at ground, because when you connect the substrate of a chip to ground, you've got a lot of connections. There's a lot of contact points, right? The problem is that when you have two wires next to one another, they have a capacitor in between them, and what will happen is that when one wire switches, it's capacitively coupled to the other wire. So, for example, when the one wire, you have two wires next to each other, and they're both at ground. When one wire switches to VDD, because you want to send a 1 bit across it, if there's a capacitive coupling between those two wires, the other wire that's currently at ground or 0 will want to come up. It'll try to pull the voltage of the other wire up. That's called, it's basically AC coupling or capacitive coupling between the wires. And so that creates an effect that's called crosstalk. And so what it ends up doing is it creates noise on wires. So what ends up happening is that you've got a wire that is supposed to be switching between ground and VDD to send ones, zeros and ones, but it's affected by other wires next to it that make it so it doesn't switch between VDD and ground. It's switching between something, there's a value above VDD and a value below ground. It also increases delay too, because it increases the total capacitance, so it makes the propagation delay slower too. But in this case, we're just worried about crosstalk. So how do you estimate crosstalk? Well, with crosstalk, you have this idea of an aggressor wire and a victim wire. So an aggressor is the one that is switching, and the victim is not switching. And so the aggressor, and this happens when not only is the aggressor switching and the victim is not switching, but you're going from a state where they're both equal to a state where they're not equal when the aggressor switches. So the voltage change in the victim can be computed as the capacitance between the wires, the adjacent capacitance, the coupling between the wires, the capacitive coupling, divided by the capacitance to ground of the victim plus the adjacent capacitor multiplied by the change in voltage of the aggressor. Okay, so you can see how the picture on the right shows you where these terms are, or what these terms are. And notice, obviously, the arrow pointing down is ground, right? And you notice that the victim is at ground. The aggressor is going from ground to VDD, is transitioning from 0 to 1, a rising edge. Now the problem though with this is that there's a couple issues. One is the amount of capacitance actually, it depends on what's going on the two wires. It's a little bit more complicated than that. So there's this idea of this Miller effect, which says that the effective capacitance it depends on what's going on both the wires. So if you've got one wire like I described, which is what's shown in this picture, where the victim is at ground and the aggressor is going from 0 to 1, then the delta V of the aggressor is going to be basically VDD, right? However, what might also happen is that the aggressor might be going from 0 to 1 and the victim might be going from 1 to 0. They might be switching opposite from one another. And if that happens, then the delta V is actually 2 VDD between the two, if they're switching opposite. And then on the other hand, they might not be switching oppositely, they may be switching together. So the effective capacitance between them actually depends on what's going on, how they're switching. The other problem too is that the other thing you have to consider is that the amount of noise that you're putting on the victim also depends on how powerfully the victim wire is being driven by its driver. So that's the problem there, is that you can also estimate the drive strength on the victim wire. So that's where you can adjust this, where this is the same equation we had before, which is the delta V on the victim is basically the capacitance divided by the ground capacitance of the victim plus the capacitive coupling between the two. So C adjacent divided by C ground plus C adjacent, and then delta V aggressor. But then they add this extra term in here, which is 1 over 1 plus K, where the K is basically a ratio of the power of the aggressor versus the power of the victim. Like, so the drive strength of the aggressor divided by the drive strength of the victim. So this is just the relative amount of drive strength, which is calculated, what is the drive strength? What have we been using to define that? Well, it's the resistance, the effective resistance, drive resistance. All our gates, if we're talking about the power of our gates, how strong they are, that depends on the width, and the width then influences the beta. The beta affects the current, and the current is what is telling you what the effective resistance. So really, we're resolving this down to resistance. And so in this case, you've got R of aggressor and R of the victim, which is shown again here, and then you can calculate this K value, which again is this ratio of power. And then, of course, in addition to the resistance, you have the capacitance, the ground, the capacitance to ground for the aggressor, plus the capacitance between the two wires, and then the denominator is the resistance of the victim multiplied by the ground capacitance plus the coupling capacitance, and so that would give you the this K factor, which, like I said, I mean, obviously, if the aggressor is driving very hard compared to the victim driver, and when I say driver, I mean whatever gate is setting the output of on that victim, is going to be more serious. So this is a simulation they show. Like, if you've got your aggressor, which is this top curve. So in this case, we're going from 0 to 1 volt. If the victim is undriven, if it's floating, then, and this is kind of amazing to me, that the voltage of the victim, even through just pure capacitive coupling, can be as high as 50%. So you might get a half a volt on that victim just through capacitive coupling. But if the victim is driven, then there's much less effect there. So victim half size will be 16%. If the victim is being driven by half-size driver, an equal-size driver, or if it's a double-size driver as compared to the aggressor, then you see almost no crosstalk, because the victim is much more strongly driven than the aggressor. So even though they're capacitively coupled, it doesn't make nearly as much difference, and it's only 4% basically of the aggressor delta V. Okay, so anyway, the point of this is that this capacitive coupling is what gives you is what's giving you noise on these wires, and the noise is something you need to consider for the noise margin. So we'll talk about noise margin next time, and then we'll move on to the next topic. So if you guys if you have any questions, feel free to send us an email, and we'll see you on Monday. Have a good weekend.